Determine the open intervals where the first derivative is positive or negative from a graph. So first off, we need to do a quick slope review. So prior to this particular class, you learned all about the slope of linear functions. You've learned that the slope is constant for linear functions. Now, what does that mean, the slope is constant? Well, that means that the slope of the linear line is going to be the same at every single point. So if we take a look at the graph here, we have 4 points on this particular graph. And if we would use our good old rise over run method here, we would see that the slope at each point is going to be 3/4. So again, the slope at every single point of this linear function is going to be 3/4. And since the slope will always be the same, that is why we were able to derive a slope formula, which we know is y2 minus y1 over x2 minus x1, or rise over run. And then that is where your conversation ended with slope in previous classes. However, in this class, we are now going to be moving into finding the slope of non-linear functions such as quadratics or rationals or exponential, sine functions, all of the above, anything that's not a linear function, we are going to talk about finding the slope of it. But the problem with the slope of these nonlinear functions is that the slope is anything but constant, meaning that the slope of the function is going to be different at every single point. So if we look at a nonlinear function, we're given 5 points here. And if we were to calculate the slope at every one of these 5 points, we would see that the slope at all these points is going to be different. So if we were to try to figure out a slope formula for nonlinear functions, that is where the problem lies, because we can't do it as easily as we could with linear functions. There is no one slope function to rule them all. However, we have briefly talked about a method to finding the slope of nonlinear functions. And then we come to the derivative. So quick review of the derivative. We know the derivative is this method that is used to find the instantaneous rate of change at a single point, i.e., finding the slope of the tangent line, i.e., finding the slope of nonlinear functions. So therefore, the derivative is used to find the slope of the tangent line by finding the instantaneous rate of change at a single point. So let's come back to our graph. So we have a quadratic function here. And if we were to come through and we were to draw tangent lines at our point, so we can go boom, hey, look at that. There is a tangent line to the point x equals 2. And now, with this tangent line, this is a linear function. Tangent lines are linear lines. So we could use our rise over run method here to find the slope of this tangent line. So we can see that we can go up 2 and over 1 and get to that point on the function, which means the slope of this particular tangent line will be 2. Now we can repeat this process again for the next point. And if we start at the point we know, we can do rise over run, so we can go up 1, and we can go over 1. And up 1 and over 1 means that we're going to have a slope of 1. And we can continue to use rise over run to find the slope of all of our tangent lines. And up here at the top of our parabola, we're going to have a slope of 0. At this particular tangent line, we could use rise over run to figure out there's a slope of -1. And then finally, with our final tangent line, using rise over run, we can figure out that this particular point has a slope of -2. So again, the derivative is the method to calculate the slopes of all the points on a non-linear graph. Alright, so from here we can now talk about determining the intervals where the derivative is positive or negative. And let's just fix my typo in there. Boom, determine the intervals where the derivative is positive or negative. Alright, so diving in, first off we need to talk about the boundary points for these intervals. So before we can find the intervals where the derivatives are positive or negative, we're going to need to start with determining what are the boundary points of these intervals. Or more specifically, where does the derivative change from being positive to negative? So, the boundary points for these intervals where the derivative is neither positive or negative. So like I just said, we're trying to figure out where the function changes from being a positive derivative to a negative derivative, and that will be a boundary point. So now we have to think to ourselves, well, if it changes from positive to negative, these boundary points can be neither positive or negative. So what's a number that is neither positive or negative? And 0! So therefore, boundary points are going to be where the derivative is 0. And we can use these points to define the intervals of positive and negative derivatives. Alright, so let's talk about this whole slope of 0 concept. Well, we know that the derivative represents the slope of a tangent line through a point. So in order to find where a derivative is 0, we're going to need to find tangent lines that have a slope of 0. So thinking back to our Algebra 2 days, or possibly our pre-calculus days, we need to answer what type of linear line has a slope of 0. I wonder if it's the horizontal lines. Yes, that's it. Horizontal lines have a slope of 0 because the height is always constant. So therefore, the derivative has a slope of 0 when we have horizontal tangent lines. Boom. It's that simple. Well, let's find out. So, where do we find horizontal tangent lines of a function? Well, as it turns out, we can find horizontal tangent lines at the turning points of a graph, or where a section of the graph is horizontal. So let's go ahead and let's take a look at two graphs. In this first graph here, we have a polynomial f of x. And we can see that for this particular polynomial, we're going to have a turning point at -2 and +3. And we can see that we are going to have a horizontal tangent line because we can just come in, and if we draw a horizontal line, it's going to intersect those turning points. So therefore, at x equals -2 and x equals 3, we're going to have tangent lines with a slope of 0 or horizontal tangent lines. Now, moving on to the second graph, we can see that we have a turning point down here at x equals 3. And again, we can draw a horizontal line and we will intersect that point. However, here at x equals 0, there appears to be a section of the graph that is horizontal. Because, if I am coming down the mountain here, I'm going to slide down, zoop, and then I have this little ledge that I can, hang out on, catch my breath and whatnot. And then I can continue sliding on down, zoop, off the screen. But anyways, since I can actually sit at this particular spot of the function, at this particular spot the function is neither increasing or decreasing, that means that it has to be 0. So therefore, at x equals 0, we are also going to have a horizontal tangent line. And beware, because these parts of the graph that are horizontal are sometimes a little bit tricky to find. They sometimes sneak up on you. They're not very obvious. But as long as we make sure we're looking for them, we should be able to find them. Alright, so now that we know how to find our boundary points, how do we actually determine the intervals for increasing or decreasing? Well, I guess it says it right on the screen. Now that we can find the boundary points, we can determine the intervals where the derivatives are positive or negative. So, since derivatives represent slope, we know the derivative is going to be positive, or the derivative will be greater than 0, means that our function has a positive slope. And if our function has a positive slope, that means the function is increasing. And similarly, the derivative is going to be negative when the function has a negative slope, i.e. when the function is decreasing. So using this information along with our boundary points, we're going to be able to determine where the derivative is positive or negative. So let's take a look at our first example here. We want to find the intervals where the derivative is positive. So, first thing we want to do on our graph is we do want to identify the x values for where we're going to have a horizontal tangent line. And again, horizontal tangent lines exist where we have turning points or a momentary horizontal pause. So looking at this graph, we're going to have a turning point at -2, and we're going to have a turning point at 3. Now, we can draw some imaginary lines in here, and we can see that these turning points are going to split up our function into 3 different intervals. One interval from -∞ to -2, another interval from -2 to +3, and then a third interval from +3 to infinity. Now, the question is asking us to find the intervals where the derivative is positive. And like we said on the previous slide, the derivative is positive when our function is increasing. Well, we can see that our function is increasing in between -2 and +3. So therefore, this would be the interval where the derivative is positive, and the other 2 intervals are out of the game because those intervals are decreasing. So therefore, f prime of x is going to be greater than 0 over or on the interval -2 to +3. There we have it. We've identified the intervals where the derivative is positive. All right, next up, we're going to look at a graph. And we want to find the intervals where the derivative now is negative, i.e. when the function is decreasing. So first things first, let's identify all turning points, and we can see that we're going to have a turning point here at x equals -3. And there are no other turning points, but there is that brief momentary horizontal pause, or a ledge in the graph. So we know that there is going to be a horizontal tangent line at that point 2, and that point happens to be at x equals 0. And just like before, these horizontal tangent lines, or points where the slope is 0, are going to separate our graph into 3 intervals. The first interval is going to be from -∞ to 0. The next one's going to be from 0 to 3, and then from 3 to infinity. Alright, so now we just need to determine where our function is decreasing. And we can see that our function is decreasing from the interval -∞ to 0, and then it continues to decrease all the way down to 3. And that's where it stops decreasing, because after 3, it increases. So therefore, the intervals for which our derivative is negative are going to be -∞ to 0 and 0 to 3. So we're going to have f prime of x is less than 0 over the interval -∞ to 0 union 0 to 3. Now, one thing I want to point out here is if you notice, I didn't include x equals 0. I did not write the interval from negative infinity to 3. Because on the graph, it does kind of appear as though that would be the interval. However, because of what we know about horizontal tangent lines, we have a horizontal tangent line right here. And that means the slope at that point is 0, and it is not negative. So that's why we can't just bump these two intervals together and create one, because it's not one interval. At x equals 0, the slope will not be negative. All right, then our final example, we want to find the intervals where the derivative is positive and negative. So we're putting both of these things together. All right, so as always, we're going to go ahead and we're going to go through and we're going to identify the turning points because that's where the derivatives are 0. And let's see, we're going to have turning points at x equals 1, 0, and about 3.5. Then we need to check for, are there any ledges? Are there any horizontal pieces of the graph? And yes, there are right here at x equals 2. So, these 4 points are going to split our function up into 4 intervals, with our first interval being from negative infinity to negative 1, and then from negative 1 to 0, from 0 to 2, from 2 to, we're just going to call it 3.5, and then from 3.5 to infinity. And I apparently had lied because these 4 boundary points split the graph up into 5 intervals, not 4. Not 4? Not 4. Wow, I'm really messing it up. Let's try to get through this last example. So, now we just need to figure out where the function is positive or where the function is increasing, and where the derivative is negative, i.e. where the function is decreasing. So we can see from our first interval, it appears as though our function is going in the upward direction, which means that will be increasing. On the next interval, it looks like we're going down the slide. Whee! So therefore, since we're going down, it is decreasing and a negative derivative. Then we need to walk back up the mountain to get to the top. And let's see, between 0 and 2, we are increasing. Therefore, we'll have a positive derivative. At 2, we got to take a little breather, hang out on the ledge. And then we'll continue climbing up the mountain. And we can see that this interval is increasing, which means it has a positive derivative. And finally, we can go down the slide right to our apparent death because we go down forever and ever and ever. Which, that's cool. Great slide, not really. But that last interval is negative. Alright, so now we just have to list the intervals. So our derivative is going to be positive on negative infinity to negative 1, union, 0 to 2, union, 2 to 3.5. Because again, we can't include 2 because at 2, the slope is 0. And then let's see, the slope is negative on the intervals negative 1 to 0, union, 3.5 to infinity. And there you have it, folks. That is determining the open intervals where the first derivative is positive or negative from a graph.